Hello and welcome to seminar number 15. Today we are going to talk about dating rocks. And what's the plan for today? An introduction into geochronology, cosmic radiation, cosmogenic radionuclides and primordial radionuclides. And then we can talk about some application, for example, the carbon-14 normal carbon-14 dating method, chlorine-36 and a little treat, iron-60 and meteorites. So let's get started. Geochronology is a field of science dedicated to dating minerals, sediments and fossils. Radionuclides in this case are a great tool because you can make use of natural isotope ratios and their deviation due to radioactive decay. Now we gotta talk about cosmic radiation. Cosmic radiation consists mostly of protons, alpha and gammas. Neutrons are not part of the primary cosmic radiation, they are part of the secondary particles of the cosmic radiation. They are created when, for example, protons hit atoms of the atmosphere and do spallation reaction, and these spallation products could be some other exotic isotopes, but also muons, neutrons or tritons or whatever. Spallation is just a sciencey word for chaotic destruction of some atoms. And these spallation products and all of this cosmic radiation, primary and secondary, account for 384 microsieverts a year from natural radiation dose. And this is the origin of the cosmogenic radionuclides. So cosmogenic radionuclides are spallation products, mostly with kind of short half-life, meaning something around some days up to some 100,000 years, which is short in geology terms. They are too short-lived to be primordial. Even some million years would be too short-lived, as the age of the Earth is around 4.8 billion years or something. And yes, these cosmogenic radionuclides are radioactive and on Earth, so there must be a way, if they can't be on here since the get-go, they have to be artificially produced, and this artificial production, well, it's kind of natural production, is the spallation in the higher regions of the atmosphere. There's a constant production rate due to cosmic radiation, and of course a cosmic radioactive decay, because they are radioactive. And these are the cosmogenic radionuclides. I marked in bold the very important ones, so tritium, beryllium-10, carbon-14, aluminium-26, chlorine-36 and calcium-41. And calcium-41 and aluminium-26, they are also important, but the other ones are really, really important. Of course, there's another classification of radionuclides that we can find on Earth naturally occurring. These are the primordial radionuclides. They are so long-lived that they didn't have time to completely decay after the Earth's formation. So they were there from the get-go and they didn't have time to completely decay. For example, we have uranium-238, 235, thorium-232, potassium-40, and there is some debate about some plutonium isotopes, but I'm not gonna go into that. We are talking about rocks today. And of course, there are also some lesser known, and when I presented it originally in the Discord server, I had them guess what I'm going to talk about. So here we have some pictures, and if you want to, feel free to leave a comment down below. And yeah, here are some tips. Maybe you get which radionuclides I mean. So this is a picture of this element, and if you can guess the element correct, that's also awesome. And if you get the complete isotope correct, that would be fantastic. So this is an element. It's the first alkaline to be stored under argon. Here we have another element, which its name has its origin in the old Latin word for Paris, not France, Paris. And here we have an element that is named after the river next to the best university, the university where I study, and another one that makes really stinky hydrogen compounds. Of course, you can pause the video on YouTube, on Discord. I just waited out some minutes, and yeah, I was talking about rubidium. Rubidium-87 has a natural abundance of 28% because primordial radionuclides are naturally occurring, so they have a natural abundance. And this one is lutetium, named after Lutetia, the old Latin name for Paris. I plagiarized that from periodic videos, and it is the lutetium-176 with a natural abundance of 2.6%. And of course, I'm studying at the University of Cologne, and the University of Cologne is next to the river Rhine, and this element is called rhenium, rhenium-187, with a natural abundance of 62.6%, meaning that most of rhenium on Earth is radioactive. Okay, it's primordial and not really active, but technically it's radioactive. And this one is tellurium, tellurium-128 and 130 with natural abundances of around 30%. Of course, there are many more, but I made a dedicated video about primordial radionuclides, so go watch that. Coming into applications, so carbon-14 and plants. I was taught that in high school in biology, and this is a very quick refresh on how carbon-14 is produced. Carbon-14 is produced when neutrons from secondary cosmic radiation hit nitrogen atoms in the atmosphere. No wonder we have 3/4 of all atmosphere is nitrogen. And this will do an NP reaction forming carbon-14, and this carbon-14 will be carried around as carbon-14 containing CO2, and this carbon-14 is taken up from plants via photosynthesis. They make some sweet sugar, and also this sugar will contain this carbon-14, and animals will eat it, and so on and so on. So there is a constant equilibrium of carbon-14 uptake from CO2 when talking about plants, and of course the decay, because carbon-14 is radioactive. And since dead plants do not do photosynthesis, there won't be an uptake in carbon-14 containing CO2, and there will only be a decay. This carbon-14 dating is based on the natural carbon-14 to carbon-12 ratio of about 10 to the power of minus 12 to 1. And deviations from this will enable you then to calculate back up to an age of around 50,000 years, 10 times the half-life. The half-life is around 5,000 years for carbon-14. Typical activities measured if you want to measure carbon-14 via an LSC, which has a efficiency of up to 100% for betas, will just be 1 decay per hour in a 1 milligram sample. So we use AMS for carbon-14 dating. Okay, talking about chlorine-36 and rocks, because rocks, they don't behave on a 5 to 50,000 year basis. They are talking about 100,000 or 2 million year basis. And chlorine-36 is a radionuclide with a half-life of 300,000 years, and it's produced via neutron capture and gamma reaction of natural chlorine-35. Of course, chlorine is everywhere, and some chlorine-36 is produced via spallation within the rock of containing potassium-39 and calcium-40. This will produce around 4,000 to 3,000 atoms per mole potassium or calcium per year, so that's not really that much. And if you want to do an analysis on chlorine-36, you would want to get rid of any interference of meteoric chlorine-36, because chlorine-36 can also be produced from argon-40 inside of the atmosphere and could then rain down on the surface of the rock. So you would have to dissolve this chlorine-36 artificially enriched surface of the rocks. You will use hot hydrofluoric acid for this, and then you could extract the chlorine-36 with silver as silver chloride, and then you would have to get rid of any other impurities, for example sulfur-36. You would then use barium nitrate to get rid of the sulfur, because the sulfur could interfere with the chlorine measurements, but I will make a dedicated video about that. Yes, this is used, for example, to understand the seismic history of different faults. We have a specialist in our university who did this analysis, and I just wanted to mention it. So if the rock is exposed to air, cosmic radiation can produce chlorine-36, and if not, chlorine-36 can decay. Yeah, you can then make use of this chlorine-36 production or decay and compare that to natural chlorine-36 levels. And this is suited for anything between 60,000 to 1 million years. Last but not least, the last application is iron-60 and meteorites. Iron-60 has a half-life of 2.6 million years. This is the more accurate one. This is a very old chart of nuclides, so 2.6 million years is the correct answer. And it's formed via neutron capture. Now, you know, iron is fusion ash, so you can't fuse iron and get some energy, but we have a very high neutron flux inside of every star. So if the star is dying, you will have a very high neutron flux, and then not only fission can happen, but also the rapid neutron capture and gamma reaction. So you can breed iron-56 to iron-57 to iron-58, 59, and 60 even. If the neutron flux is high enough and it doesn't decay into cobalt, you can then force it to be iron-60, and then you have iron-60 in stars. Why is that important? This is important for modeling the formation of planets. Let's make the assumption iron-60 is distributed heterogeneously in the protoplanetary disk, meaning that this is the protoplanetary disk, and you will have some areas with more iron-60s and some with less iron-60. So let's say that. Due to iron-60 injection from a supernova nearby, so you have a supernova here and exploded, and it spread some iron-60 into this disk, and it did that because it happened here more than it did here. Yeah? This would mean that if we have meteorites forming alongside other planets, that the meteorites that formed here would be iron-60 deficient. Of course, we are not talking about just iron-60. We can't measure iron-60 directly because it's long decayed, but it will decay into cobalt-60 pretty much instantaneously, just 5,000 years, into nickel-60. And then we would expect to have some meteorites with higher nickel-60 content, meaning that they were formed here, and some with lower nickel-60 content. And if we look at the measurement, this is not the case. This supports another idea, talking about how the protoplanetary disk was formed. This protoplanetary disk was formed from the collapse of a pre-solar molecular cloud. And this could be triggered by the interaction with a nearby star, so with a supernova. So the supernova happened, injected some iron-60, and both of these factors kind of triggered the collapse and the formation of a protoplanetary disk, meaning that the whole protoplanetary disk, since it was formed from the pre-solar molecular cloud, has a homogeneous iron-60 distribution because it just formed also because iron-60 was injected. So this trigger event from the supernova nearby. The protoplanetary disk was only formed because the pre-solar molecular nebula was collapsed by this supernova that also happened to inject iron-60, if that makes sense. Yeah, and if you can see, there is pretty much every meteorite that we can measure here has the same nickel-60 content, meaning that this iron-60 distribution was homogeneously. Okay, that was really quite some tough stuff, even for me to say that in English, because I'm native German. And yeah, if you understood even just 1% of the last slide, I'm quite proud of you. Here's a picture of such a molecular cloud. And let's see, might be collapsing into a protoplanetary disk if a nearby supernova happens and also injects some iron-60 alongside it. So with that being said, thank you for your attention and goodbye.